Hello, if we shine a laser beam through a double slit, we get a double slit interference pattern. If we shine a laser beam through a diffraction grating, we are going to get the diffraction grating interference pattern. I'm sure you noticed that the grating produces a pattern which is much more spectacular, much brighter, right? And did you also notice that the fringes are more spaced out compared to the double slit? So in this video, I'm going to explain why. Now, the double slit, as its name suggests, is just two narrow slits. In fact, when I zoom into this, I could literally see the two narrow slits. But what is the grating? It looks pretty transparent to me. And when I zoom in, it still looks pretty transparent. So what you see here is the artist's impression of what a grating is. Basically, it's many hundreds, thousands, millions of slits which are equally spaced out. Now, it's very important that they are equally spaced out, yeah? If not, the analysis will be very difficult. So double slit, two narrow slits. Grating, thousands and thousands of many narrow slits equally spaced out. Let's talk about the bright fringes first. So for the double slit, we have slit A, slit B. So when the path difference d sine theta is equals to 0 or 1 lambda, 2 lambda, 3 lambda, and so on, the two rays will arrive in phase, superpose constructively, and give you a bright fringe. So remember, the condition for bright fringe for the double slit is d sine theta is equals to n lambda. Now what about the grating? So I have slit A, slit B, slit C, slit D, E, F, G, and so on. So there are thousands of slits, yeah? But I'm only drawing 3 in this diagram. Remember, they are equally spaced out. So the slit separation between A and B is D, between B and C is D, between C and D is D, and so on. So if the path difference between A and B is d sine theta, then the path difference between B and C is also d sine theta. Between C and D will also be d sine theta, between D and E, E and F, and so on. So basically, every adjacent slit have the same path difference. So if d sine theta is equals to 1 lambda less, then the path difference between C and A will be 2 lambda, and the path difference between B and A will be 3 lambdas, and so on. So B and A will arrive in phase because the path difference is 1 lambda. But C and A will also arrive in phase because the path difference is 2 lambda. B and A will also arrive in phase because the path difference is how many? 3 lambdas, and so on. So in fact, every ray leaving every slit will arrive in phase together. So what do you get? I will call it a super constructive interference. So for the grating, when do we get bright fringes? We get bright fringes when d sine theta is equals to n lambda. Same condition as the double slit. But then for the double slit, it's only 2 rays superposing constructively. Whereas for the grating, you have thousands and thousands of rays superposing constructively. That's why I call this a super constructive interference, which will form a super brighter than bright fringe. Okay, now let's talk about the dark fringes. For the double slit, you get a dark fringe when d sine theta is equals to half lambda, 1.5 lambda, 2.5 lambdas, and so on, right? What about the grating? Now, let's say the path difference between B and A is 0.01 lambda. So that means the path difference between C and A will be 0.02 lambda. Right? Because you have 0.01 lambda here and 0.01 lambda here. D and A will have a path difference of 0.03 lambda, and so on. So do these two rays destroy each other destructively? No, right? Because the path difference is only 0.01 lambda. But then remember, there are thousands and thousands of slits in the grating. So even though this one and this one are off by only 0.01 lambda, surely somewhere down along the grating, you can find somebody who has a path difference of 0.5 lambda. Similarly for B, somewhere down you can find a ray which has a path difference of 0.5 lambda with B, and so on. So do you get the idea? Even when d sine theta is a small fraction of a half lambda, because we have so many rays here, we are going to have a lot of destructive interference. So what's the result? All these rays will basically destroy one another. Even if they don't destroy each other completely, there's enough destructive interference occurring to make the outcome pretty dim. So for the grating, when do dark fringes happen? Well, it practically happens all the time, except when d sine theta equals to n lambda, because that's when you have the super constructive interference. All the other path differences, you're going to get dark fringes. That's why for the double slit, you get a bright fringe when path difference is 0 lambda, dark fringe when the path difference is 0.5 lambda, bright again at 1 lambda, dark again at 1.5 lambda, bright again at 2 lambda, and so on. However, for the grating, you have a super bright fringe when the path difference is 0, but you don't have to wait for the path difference to reach 0.5 lambda before you get a dark fringe. As long as the path difference is a bit more than 0, you get the dark fringe already. Until when the path difference is 1 lambda and then boom, you get a super bright first order bright fringe. And once the path difference is slightly more than 1 lambda, maybe 1.01 lambda, well, you get the dark fringe again. And then super bright again only when it's 2 lambda path difference. Pretty cool, right? Okay, now let's look at the two interference patterns again. Now, since the bright fringes are formed at the same condition when sine theta is equal to n lambda over d, why is it that for the double slit, the fringes are formed so close together, whereas for the grating, they are formed at pretty large diffraction angles? Well, it has all got to do with the dimensions of the slits. Now, for the double slit, we have only 2 slits. So there's a limit to how narrow we can make the 2 slits to be. Because if the slits are too thin, the total amount of light passing through the 2 slits will be too little. So even with constructive interferences, the bright fringes will be still too dim. So we have no choice, we have to make them at least of a certain width. And because of that, the slit separation cannot be too small. The slit separation is measured from the center of the slit to the center of the slit. So if you want the slits to be of certain width, then there's a limit to how close you can make the 2 slits to be. The grating has no such a problem because we have thousands and thousands of slits there. So even when we make the slits very, very narrow, we still have enough light passing through the grating to give us a very beautiful and bright interference pattern. So as a result, we can pack the slits really, really close together. So the bottom line is, the slit separation for the grating is much smaller than the slit separation for the double slit. And this of course will have an effect on where the fringes are going to be formed. For the double slit, lambda over d is usually pretty small. So because of that, the bright fringes are usually formed at a small diffraction angle theta. So what I sketch here is the graph of sine theta going from 0 degrees to 90 degrees. So the bright fringes are formed when sine theta is 1 lambda over d, 2 lambda over d, 3 lambda over d, and so on, right? So because lambda over d is small, the fringes are all formed at small angles. Whereas for the grating, because the slit separation can be made as small as 1 micron even, close to the wavelength. So the lambda over d for the grating is quite big, and because of that, the fringes are formed at larger diffraction angles. That's why the bright fringes for the grating are so spaced out. Now the graphs can also explain why the double slits fringes are regularly spaced out. Because when the fringes are formed at small angles, we are at the portion of the sine graph where it's pretty straight. So the fringes are equally spaced out. But for the grating, the fringes are formed along the curved part of the sine theta graph already. And because of that, you can see that the fringes are not equally spaced out. In fact, the spacing gets larger and larger. Now, do you understand what you're seeing here? For the double slit, because the slit separation d is usually not that small, the fringes are formed at very small angles and they are regularly spaced out. Because of that, we usually don't even use the d sine theta is equal to n lambda formula to do the calculations for double slit. We use the easier formula, which is the formula for fringe separation. Whereas for the grating, the fringes are formed at large theta, which means they do not have a constant fringe separation. Because of that, we have to use this formula, d sine theta is equal to n lambda, to calculate the positions of every fringe. Alright, that's all. Ta-ta!